So I'm a reactor systems design lead, and I work at Rolls-Royce SMR. Now SMR stands for Small Modular Reactor, and what our project is trying to do is design and construct a new fleet of nuclear power stations to support the UK in providing, net zero clean energy. Now, as a reactor system design lead, I'm responsible for leading a small team of engineers who designs and develops some of the fluid systems that we use as part of the nuclear power station. So one of the key interactions with that is I'm the owner of the chemistry control system. So going around a nuclear reactor, you've got coolant, which is water in our case, and the system that I look after is used to add chemicals to the coolant to make sure that all of the properties, all the properties of the materials are kept in line. I'm a design engineer, so it's an office job. I spend my time between meetings, workshops where we're trying to solve problems, and doing calculations about what the design is going to look like. So what I will produce and what my team will produce at the end of any particular phase, a series of design reports which say our system needs to look like this. It might be diagrams, it might be written reports, it might be part of a safety case. So a standard day I'll flip between sort of team meetings, maybe a workshop, and then going on to sitting down and doing some design myself, doing some calculations and writing those up in a report. It's a way that I can use the analytical skills that I learned through, college, university. I'm an engineer by training, a chemical engineer, and applying that to something which matters to the world. So we're trying to do what we can to support net zero and preventing climate change, clean energy. And I think the bit I enjoy the most is seeing how the skills that have developed, technical skills, allow me to help towards that. It's also really interesting that, you're looking at fundamental science and seeing how that applies to the real world. I'm taking some of the concepts that, I'd studied at university and then using them to size this huge system that's going to produce clean energy. So yeah. I studied maths, physics and chemistry at A-level and went on to study chemical engineering at the University of Manchester. If anyone doesn't know what chemical engineering is, it's really the science of taking any sort of reaction that you've got on lab scale and then scaling it up. So understanding all the heat transfer that you might get in taking that, laptop experiment and then turning it into an industrial process. Almost everything that you come across in your day-to-day lives, whether it's like the plastic or the metal of your mobile phone, there's been a chemical engineer that's been involved in that process of really designing the chemical plants that go and produce that. So that's sort of my background. I'm working as a nuclear engineer, like a reactor system designer. So what I do is apply the concepts that I learned through that chemical engineering degree to design the process or the system that cools the nuclear power plant, and in my case controls the chemistry, controls the composition of the coolant that we're using. So our system has a lot of tanks, and we'll dose different chemicals into the plant in order to keep the coolant within a particular specification. So say, so many parts per billion of ions, or maybe we're trying to control the pH of the solution. And we monitor that through the life of the system. And really what I'm doing is I'm designing the system to be able to cope with whatever anything's thrown at it later down the life cycle. My team recently, we've been looking at sizing some of the ion exchange columns that we use as part of the system. So if you can think over time, as coolant goes round the nuclear reactor circuit, you get build-ups of impurities. that, you know, come off some of the metallic materials. So you've got things like heat exchange in there, really just a series of pipes. And it accumulates with particulates, you know, metal particulates. Now, as that goes through the core of the nuclear reactor, it becomes irradiated, and it's important that we clean out some of those impurities. And the way that we do that is we use an ion exchange column. And what you're talking about really here is a big sieve that will extract from the coolant all of those impurities and trap them onto the resin beads. Now, in order to size how large these ion exchange columns need to be, you have to go in and look at the specification. So I need to keep the amount of impurities in there below a certain quantity. I need to look at the surface area of the ion exchange column beads that we have, and I need to look at the effectiveness of those beads. So I'll go to a supplier and I'll say that I can remove so many kilograms of particular impurity per minute. And in order to size the column itself, you need to understand what's going on throughout the cycle of the reactor. So you have to understand all of the chemical reactions that are going on over the life cycle, and then model those. So you can see at any one point, maybe a certain ion is increasing, and then later in the period, a certain one will be decreasing. And we size the columns on the basis of that chemistry modeling in order to basically find the optimum design. It can help you in two ways. So it can help you if you want to go down a technical route, and opens up a whole bunch of careers in pharmaceutical industries, engineering, life sciences. There's a huge array of different careers out there, but really interesting ones actually that you don't really come into contact with unless you've known somebody in the sector. You'd be surprised by how many different jobs there are out there, and I'm sure you'll see some of those through the course of all these films. So that's one side of it, that it opens up a really wide variety of careers. The second reason is I think it just gives you that really broad analytical mindset, which is something that is applicable to really any career that you want to do. And even if you don't want to go down a really, hard science route, it can allow you to really understand about the world a little bit more and be really interesting as well. Like, A-level chemistry is challenging, but it's also really interesting and really rewarding. And I think it's something that could be really valuable for for somebody to study, even if you're not wanting to do something really technical at a high level.